Hello, everyone, and welcome to today's webinar, Analytical Challenges in Developing LC-MS Methods for PFAS, which is part 2 of our 3-part series on PFAS. My name is Alex Nase from MacMod Analytical, and I will be moderating today's webinar. I just want to remind you that if you have any questions during the presentation, please type them into the chat and include your name and company. We will answer as many as possible during the Q&A session at the end of the presentation. If you miss anything or would like to review the content, you will be able to watch a recording of the webinar and view the slides on MacMod's website, and we will also send out a follow-up email with links to the recording and the slides. You can also find a collection of our past webinars and resources on MacMod's website, including part 1 of this series if you missed it. Now I'd like to introduce MacMod. MacMod is a chromatography company that offers scientists innovative solutions for their complex separation needs. We recommend and supply the best columns and accessories to our customers. We also provide application notes, technical reports, white papers, and other up-to-date resources from industry-leading scientists to keep you informed. Now I'd like to introduce our speaker, Matt James. Matt earned his PhD at the University of Bristol, and over the last 15 years he has worked within the technical support, applications, and R&D teams at Hichrom, which is now part of Avantor. His recent focuses have included HPLC and UHPLC method transfer and translation, the use of solid core phases, development of next-generation LC stationary phases, and the development of LC methods for key applications such as the analysis of nitrosamines and PFAS by LC-MS MS. Thank you for joining us today, Matt.
Thank you for the introduction, Alex. Welcome everyone, and welcome back to those of you who joined us for part 1. In this series, we're going to focus on the LC-MS analysis of PFAS, and the aim is to try and really share some of the thought processes and experience that we've gained in our application lab when developing various methods for the analysis of PFAS. To start, I want to again say a quick thank you to Alex and our friends at MacMod Analytical, who are our US distributor for chromatography supplies, who we've worked very closely with for many years ago, for hosting us for this webinar series. So in part 1, we ran through some of the key background aspects of PFAS analysis, and today we're going to move on and take a closer look at how LC-MS provides a key solution for PFAS analysis. So primarily the discussion today is going to focus on analysis using triple quadrupole instruments, but many of the concepts I'm going to discuss are very much applicable to high-res approaches too. And then in part 3 in a few weeks' time, we're going to move on to one of the key aspects of working with PFAS, which is how to tackle and control background laboratory PFAS and prevent them from interfering with our analyses. So to employ LC-MS for PFAS analysis, we need to consider a number of key challenges. So firstly, the high sensitivity that we require, which, as we discussed last time, is largely driven by regulatory limits, which require analysis in the parts per trillion or nanogram per liter range. For example, drinking water in the US, we have the National Primary Drinking Water Regulation, which dictates that for PFOA and PFOS, maximum contaminant level allowable is 4 parts per trillion, and 3 other PFAS have slightly higher limits of 10 parts per trillion. These limits are, of course, very low, so that very much dictates that we need highly sensitive analytical techniques such as LC-MS. In addition, an additional challenge is the presence of background PFAS, and this applies not just to the analysis itself, but also to the collection, storage, and transport of samples as well. So unfortunately, in terms of the lab, the use of PFAS and PFAS-containing materials can be quite widespread. So for example, the use of materials such as PTFE. And clearly, we therefore need to avoid using any equipment or consumables that contain PFAS, as otherwise we risk compromising the sample's integrity. Additionally, PFAS may be used in the production of equipment and consumables, say, for example, lubricants and various release agents that may be used for processes such as injection molding or extrusion could potentially contain PFAS. And finally, PFAS may also be present in the solvents that we use for our analysis, and indeed the analytical instrument itself. So clearly this is quite a substantial issue, and we're going to touch on this a bit today and delve into it in more detail in part 3. Additionally, as we mentioned last time, we have a very wide range of target analyte structures with very different physicochemical properties. So we need to ensure analytical techniques have good coverage and recovery of our target analytes. And we also potentially have to deal with a wide range of target matrices. So example ranging from simple matrices such as drinking water all the way to soil, sediments and biomatrices. Analytical methods based around LC-MS provide a powerful solution to many of these challenges. So firstly, they're very sensitive and are typically at least 10 to 100 times more sensitive than UV detectors. The data here, which we discussed in part 1, shows that these parts per trillion down into the parts per quadrillion detection levels can be readily achieved, especially if we employ sample pre-concentration by using solid phase extraction. Mass spectrometers are also very specific. We have the ability to tune into unique masses and target compounds, and it provides a very rapid means of analysis, although data collection rates can be potentially limiting for complex analyses where we are looking to monitor a large number of MRM transitions. Often coelution is not so much of an issue due to the specificity of the mass spectrometer, although we do of course have to be wary of isobaric interferences and the potential for ion suppression that can occur due to other species or matrix components coeluting with our target analytes. There are, of course, a few downsides to LC-MS analysis. The initial instrument purchase is, of course, many times higher than that of other detectors, and the operational costs are much higher as well, with more servicing requirements. The level of training required for the analyst is also considerably higher, and the LC-MS methods themselves are fairly complex and can take a substantial amount of time to develop too. But overall, the mass spectrometer can be routinely employed as probably the most comprehensive approach to PFAS analysis. So I'm now going to move on to take a closer look at the LC-MS methods themselves and how we go about developing new methods, and also some of the considerations that we need to employ for PFAS analysis that help us deal with some of the issues around background contamination or background interference from our analytical instruments. So LC-MS is typically the most widely utilized approach for PFAS analysis, with triple, quadrupole, ion trap, and time-of-flight mass spec methods widely utilized. Here I'm primarily going to look at tandem mass spec performed with a triple quadrupole instrument, as this provides us with a powerful technique for the quantitative targeted analysis of a specific set of target PFAS compounds, and very much provides that high level of sensitivity that we require. Now, before developing any LC-MS methods, and this isn't just limited to PFAS, we highly recommend assessing the physicochemical properties of our target analytes, as this can very much guide the method development process and helps us to define key parameters for the method. If we begin by considering PFOA, here we have a plot of the distribution of the neutral and the negatively charged deprotonated species as a function of pH. And we can clearly see that above a pH of 2 or so, we really have primarily that ionic species present. This means that we look to operate our mass spec in the negative ion mode for PFAS, and the deprotonated species also have significantly reduced hydrophobicity, which is important for good coverage of longer chain PFAS using reverse phase liquid chromatography approaches. The pKa does shift somewhat towards slightly higher pH for some of the other functional groups encountered, such as the sulfonamide group, where we have a pKa of around 3.5. To maintain those compounds in the negatively charged state for detection and reduce their hydrophobicity, we would ideally have a mobile phase pH of about 6. So it's fairly common to see ammonium acetate used as the buffer, which has a pH of around about 6 or so. And here, the majority of our analytes will be in that negatively charged state. The fact that our analytes are ionizable with moderate masses and that we have a number of quite hydrophilic short-chain PFAS means that electrospray ionization is typically used. For the chromatographic separation, we saw last time that we have quite a wide range of hydrophobicities for our target analytes, for which reverse phase chromatography is suitable, but we need to employ gradient elution for sure to achieve successful retention. Another structural aspect of PFAS analysis that I just want to touch on quickly is that many PFAS will actually be present as a mixture of linear and branched isomers. PFAS are manufactured using either electrochemical fluorination or telomerization. Now, whilst the telomerization process produces primarily straight-chain PFAS, The ECF process actually produces a mixture of linear and branched PFAS. So for example, PFOA produced by ECF typically contains around 78% of the straight chain PFAS and 22% of the branched isomers. And it's common to see this reflected in our sample composition, although many studies have demonstrated that the different physicochemical properties of these isomers actually means that depletion or enrichment in certain matrices may be encountered. So typically from a chromatographic point of view, the branched isomers tend to elute first, and we'll often see a series of closely eluting peaks that may co-elute that correspond to the different structural isomers present. Many published methods will actually require chromatographic separation of these isomers, and as we can see on the screen, this is relatively easily achieved using the conditions that we're going to go on to discuss in the next few slides. One important point to note is that for many methods, so for example, EPA methods, we actually integrate all the isomers as a single peak. So it will be important to verify that integration parameters used within the data acquisition software achieve this, unless, of course, you wish to separately quantify and study those different isomers. So as we mentioned, ammonium acetate is commonly used as a buffer for PFAS analysis, and this is a very nice volatile buffer. It's fully compatible with mass spectrometry, and you'll typically find that many methods tend to employ buffer concentrations of around 5 to 20 millimolar. You'll find that for many methods, methanol is used as the organic modifier, but for some of the more hydrophobic PFAS, we tend to use acetonitrile instead. And this is shown in these chromatograms on the screen, where we have 40 PFAS compounds separated on the same gradient conditions using the same column with either methanol or acetonitrile as the organic modifier. And you can see in the case of methanol, the final compound diluting is perfluorododecane sulfonic acid, or PFDOS. However, when we switch to using acetonitrile, we can actually see that there are a few additional PFAS compounds within the sample that weren't eluted with methanol. And so if you're looking to detect a broad range of PFAS, including some of the more hydrophobic ones, you're very much going to want to consider using acetonitrile as the organic modifier. If we now switch our attention to the stationary phase that we're going to use for gradient separation, as we mentioned, we're going to be using reverse phase chromatography, and therefore a C18 stationary phase has become quite routinely used for many PFAS applications. One of the challenges of analyzing PFAS by reverse phase is the fact that, as we saw earlier, a lot of the shorter chain PFAS have very low, often negative log D values, and so obtaining good retention of short chain compounds on a reverse phase column can be somewhat challenging. From column screening work that we've carried out, we do actually find that the C18 phase tends to provide the best retention for these compounds, and that other stationary phases don't tend to offer much in the way of useful selectivity. So at the current time, the C18 phase is very much our favored stationary phase choice. Another consideration when it comes to column selection is the particle morphology. We can either look to use fully porous silica particles or solid core particles. Here on the screen, we've got a comparison of an A6L 3 micron C18 fully porous particle and an ultra core 2.5 micron superficially porous particle or solid core particle. And as we can see, the solid core particles provide less retention for PFAS than the fully porous particles, even though our separation conditions are identical. This is because, firstly, the solid core particles consist of a solid core surrounded by a fully porous layer, and therefore there is less stationary phase for our PFAS to interact with for retention. Secondly, solid core particles have decreased permeability compared to fully porous particles, which again leads to a reduction in retention, and this could be problematic for some of those early eluting compounds. We can, however, see that in this case, using a 2.5 micron solid core particle does give us narrower peaks and an improvement in peak height. So there is a trade-off between the two, but generally speaking, in our experience, we've opted towards using fully porous particles to maximize the retention of those early eluting PFAS compounds where possible. An additional aspect of our LC system setup that we need to consider is that because of the ubiquitous nature of PFAS compounds, the solvents buffers that we use for a mobile phase, along with components of our LC system, such as solvent lines and solvent bottles, may contain some degree of PFAS. Essentially, if we consider a standard LC setup, which is shown in the diagram here, any PFAS contained within the mobile phase, the degasser, the pump, the mixer, or the injector will accumulate that on the head of our analytical column when we equilibrate it before sample injection. When we begin the gradient, those PFAS will elute from the column and be detected by a mass spec. And here we have an example from our own LC system when we first began PFAS analysis, which showed that when we ran a blank run with no injection, we see 6 PFAS compounds eluting from our column. And of course, if we inject an actual sample, those background PFAS peaks will correlate with the PFAS in our sample. And this is shown here. So in chromatogram A, we perform a blank run and we see a peak for PFOA, which originates from our LC system. If we inject a sample containing PFOA, as shown in chromatogram B, this background peak overlaps with our sample peak, leading to inaccurate quantitation of our target analyte. There are several approaches that we can use to deal with this. So firstly, instrument manufacturers will generally recommend replacing certain system components, such as solvent lines, with non-PFAS containing equivalents. The most important approach that really I would say is mandatory for all PFAS analysis is to use a delay column. The delay column is fairly unique to PFAS, and essentially it's a smaller column which we install immediately before the sample injector. The delay column will trap any PFAS from the mobile phase, and these will be eluted separately from our sample peaks. So if we move from chromatogram A, our blank run with no direct column, to chromatogram C, where we've now installed the delay column, you can see that the background PFOA peak is now eluting later as a much broader peak. If we now inject a sample, as shown in chromatogram D, our sample peak is now well separated from the background PFOA, which means that we can accurately quantitate our target PFAS. One thing, if there's one thing that you take from this webinar, is really, I would say that the use of a PFAS delay column is absolutely essential for PFAS analysis to prevent false positives and allow accurate quantification of your target analytes. So one quite critical part of the LC method is the sample injection volume. We want to reach very low detection limits, so a logical thing to do would be to increase the injection volume to improve our sensitivity. However, as we mentioned earlier, we have to use high percentage of organic solvent in our sample diluent, and this places limitations on the sample volumes that we can inject onto our LC system. Ideally, we want to inject with a weak solvent, so a highly aqueous solvent, but this is just not possible for PFAS. What we find is that with the high percentage of organic in our sample diluent, the peak shape of early eluting compounds can become distorted or even split as we increase the injection volume. So here we've got an example of 4 PFAS in 96% methanol injected onto a 10 by 2.1 millimeter ID column. If we look at PFOA and PFPA, we can see that as we increase the injection volume, we increase peak height and the peak shape isn't really affected. However, for PFBS and PFHXA, which elute earlier, we find that the injection volumes of 1 to 4 microliters are fine, but as we move to 6 microliters, you can maybe just about see that the PFBS, we start to have some distortion of the peak shape, and then as we move to 8 or 10 microliters, we completely lose the peak shape. So the requirement of using high organic in our sample diluent means that we need to be very careful and carefully consider the injection volume, and we'll touch on that aspect more a bit later on. We mentioned earlier that sample pre-concentration using SPE is widely used to increase sensitivity, but another approach that's increasingly being used, particularly given the high sensitivity of modern mass spectrometers, is direct injection. So for some methods, a dilute and shoot approach where the sample is filtered or centrifuged and then diluted with an organic solvent and then injected onto the system may be feasible. The direct inject approach is not as sensitive as the SPE approach because, of course, we don't have that sample pre-concentration, and of course, we're diluting our sample, but it's a lot faster, a lot simpler, and has less potential for sample contamination during the sample prep process. However, one point I want to make about this sort of approach is that the percentage organic used in the final injection sample is absolutely critical. And this is shown on the graph here. So here we have a plot of the percent organic in the sample diluent versus the percentage response in 100% organic. And as you can see, above 60% organic in our sample diluent, methanol is a solvent in this case, we generally see 90% of our expected response for most of our PFAS. However, as you move to 50% and then drop down to 40%, you can see that while some of our early eluting less hydrophobic PFAS, such as Adona and PFBS, show 100% response, the longer chain PFAS give much lower response. So really, if you're looking to use the direct inject approach, you need to maintain at least 50%. I'd say more like 60% organic solvent in your sample diluent. So now we've discussed the basics of performing LC-MS analysis for PFAS. I just want to finish by taking a look at some example applications where we apply some of the concepts we've just discussed. So we have here the separation of 25 PFAS using EPA method 533 for drinking water. So here we need to be working at that low parts per trillion level. We use the 10 centimeter Avantor ACE 3 micron C18 column, and we also use that PFAS delay column that we mentioned earlier. Ammonium acetate is used in line A and methanol as the organic modifier in line B. And this chromatogram shows the separation obtained using the gradient program as it's stated in the EPA method. Here the sample diluent is methanol water 80/20, so we use the 5 microliter injection volume. Data here is for a standard solution with concentrations ranging between 100 to 2,500 nanograms per litre. Now EPA 533 utilizes SPE to incorporate a 250 times sample pre-concentration during the sample preparation. So that concentration range actually corresponds to 0.4 to 10 nanograms per litre in the actual sample itself. So we're readily achieving the low parts per trillion level analysis that's required. This standard method has a fairly long gradient program, 25 minutes, and we also have to re-equilibrate the column afterwards. So the cycle time for the method would be around 40 minutes long. Now, the nice thing about the EPA methods is that they allow you a lot of flexibility with the chromatography side of the methodology. By utilizing a slightly higher flow rate of 0.4 mils a minute and a simplified 5 to 95% gradient, we're able to perform the analysis in under half the time as the standard method. So here we have a total cycle time, once we've re-equilibrated the column, of around 17 minutes. Increasingly, we're looking to analyze a broader range of PFAS compounds as analyses move away from focusing on legacy PFAS, and new and emerging PFAS are becoming of increasing concern. So EPA method 1633, which covers the analysis of PFAS in aqueous, solid, biosolid, and tissue samples, incorporates a total of 40 PFAS and includes several of those shorter chain compounds that are difficult to retain by reverse phase. So here we have 96% methanol in our sample diluent, so we've decreased the injection volume slightly to 4 microliters to avoid any issues with peak shapes for those early eluting components. Again, by adapting the gradient method, we can achieve this separation in around about 10 minutes. This time, of course, using acetonitrile as the organic modifier to elute those more hydrophobic components in this sample. One point that's worth making is that our mass spec source parameters are different than the previous application. And in general, it's worth optimizing all mass spec and compound parameters for your system as we're looking to achieve such low levels of sensitivity. So taking the time to tune up your mass spec for your individual application rather than taking parameters from the literature or an existing application note is certainly a worthwhile exercise. Finally, here we have an example of the separation of 18 PFAS compounds together with isotopically labeled standards for EPA method 537.1. Again, drinking water sample method that utilizes that 250-fold sample pre-concentration step. For this particular method, we have quite tight criteria for the peak shape of the first eluting peaks. So here we've opted to lower the injection volume to 1 microliter and adapt the start of the gradient program to reliably meet those criteria. Despite the small injection volume, you can see here for this sample, which corresponds to 4 parts per trillion concentration in the samples, we were readily able to quantify down to the levels required by the regulators. This method achieves excellent accuracy and linearity for calibration curves, and here we've got an example for a donor, which we've calibrated down to a concentration of 20 parts per quadrillion, well below the regulatory requirements with an accuracy of 110.7%. Also shown are the accuracy and precision for 6 QC samples, which again highlight the reproducibility of this methodology. And finally, I just want to highlight a slightly more novel approach that we've taken. This is with an experimental rapid analysis that we performed with a short 1 centimeter long column. The idea behind this application was to provide a rapid analysis method with a dilute and shoot approach to rapidly pre-screen water samples to identify those with high PFAS load. The reason may want to do this is so that the high PFAS load samples could be diverted to an alternative sample preparation workflow so that we don't have any risk of cross-contamination or carryover with samples containing trace levels of PFAS. Here we inject the sample in 50-50 methanol water and we complete the entire analysis in a time of 1.6 minutes. So finally, to conclude, hopefully we've shown today how LC-MS is a powerful tool for the determination of PFAS, and it can very much be applied to a variety of different sample types. We've run through various key considerations for developing methods. So firstly, considering the analyte physicochemical properties is very useful, and this can help guide method development. And I just want to reiterate this is an extremely valuable approach for any chromatography method development. We've seen that C18 phase tends to be the column of choice and that ammonium acetate is often used as the mobile phase buffer. And the choice of using either acetonitrile or methanol as the organic modifier really needs to be driven by the hydrophobicity of the compounds that you're looking to analyze. One of the most important things to remember when developing LC-MS methods is that it is really absolutely essential to use a delay column for PFAS analysis in order to remove any background PFAS from the mobile phase that may otherwise interfere with the analysis. And it's important to remember that that needs to be plumbed into the LC-MS system immediately prior to the injector. We also need to pay careful attention to injection volume due to the use of high organic content diluents. And we also need to consider that diluent competition very carefully if we're looking to start moving towards direct injection approaches. And finally, we've run through a variety of applications that we've worked through in our lab that help demonstrate some of these points. As a reminder, we've got a variety of literature and resources available regarding the topic of PFAS analysis. So of particular note is the technical note shown on the left-hand side, which gives a lot of detail and explanation around the requirements for the use of that delay column in the analysis of PFAS. And we also have a variety of application notes available as well, demonstrating or detailing a lot of the applications that we've seen today. And those can all be downloaded from MacMod's website. So finally, thank you very much for attending this webinar today. I hope that it's been useful and that the topics we've covered will prove valuable for implementing PFAS methods within your own labs. I very much look forward to the final webinar in this series, where we'll move on to look at perhaps one of the biggest challenges with PFAS analysis, which is how to identify and deal with potential background contamination that can occur during our analysis. So once again, thank you, and I'm happy to answer any questions.
Thank you, Matt, for that wonderful presentation. As Matt just alluded to, we'll now move on to the Q&A. Just a reminder that if you do have any questions, please type them into the chat window. Include your name and company if you can, so that if we don't have time to hit all of the questions, we'll be able to respond to you. So our first question for Matt is, can you explain the baseline drift from compound to compound in application 1?
Yep, sure. So I'll just move back to the that first application quickly. So yeah, you can see there's a little bit of variation in the level of baseline that we have for the individual compounds, and we do find that for some of the transitions, we do tend to have a lot more baseline noise than others. Quite often that tends to be more for some of the lower molecular weight analytes. The transitions that we're monitoring are sort of less specific. There's more likely to be a bit of sort of background interference there. So PFBA, for example, the earlier soluting compound is one that we do have a very high or tend to have quite a high level of noise for with the various methods. So yeah, hopefully that sort of explains quite why there are different levels of background. Some of the higher molecular ones, higher molecular weight ones, so some of the chlorinated species, for example, we tend to have almost non-existent baselines. The transition is so specific.
Okay. The next question, could you give some advice on how to connect the delay column to the HPLC system?
Yeah, so the key thing with the delay column is to connect it immediately before the sample injector. So that's just to make sure that any background PFAS from the mobile phase or the other instrument components like the degasser, the pump, etc., are trapped on the delay column. So in our specific LC system, the outlet of the mixer feeds directly into our autosampler via a short length of stainless steel tubing. So we simply disconnect the tubing there, plumb in the connect the delay column to the autosampler, and then use a short length of stainless steel tubing to connect the column, the delay column inlet back up to the mixer. One other point it's worth considering is that because the delay column is being installed before the analytical column, that's the high pressure end of your system. So whatever your tubing and connectors you do use to connect that need to be capable of withstanding the pressures you're going to reach. So for example, if you're using an analytical column that's packed with sub 2 micron particles, you're going to need to use tubing and fittings that are rated to higher pressures than if you were using a 3 micron, but in general avoid any peak tubing or finger tight fittings for making those connections, I would say.
Thanks, Matt. Next question. Do we need to separate individual branched isomers or just the branched and straight chain isomers?
So some of the methods do sort of specify that you need to achieve separation. So some of the EPA methods, for example, I think it's 537.1, suggest that you use a PFOA, technical grade PFOA standard to verify the separation of linear and branched isomers. In general, it's a little, I think this sort of area is evolving. I think as it's sort of increasingly being recognized that the branched and linear chains need to be separated and potentially quantified separately. But the thing is, you need the standards that contain both the branched and the linear isomers to be able to accurately quantitate. So again, a lot of the regulated methods sort of say that you're not able to, or you must have a calibration standard that contains the different isomers in order to actually quantify them. Yeah, it's an area that I think we'll sort of see a lot of more people getting interested in now. The branched and linear isomers, they do behave quite differently within the environment, within different matrices. So yeah, it really depends on what sort of standards you're working with as to what you can actually quantify for a lot of methods.
Okay, unfortunately, that is all the time we're going to have for today for questions. If you did send a question that we did not have time to get to, we will follow up with you via email. Just a reminder, we will also be sending a link of the recording and the slides later on this week. I want to thank Matt again for a wonderful presentation and want to remind you that we do have a third part of this series upcoming, tackling and controlling background laboratory PFAS, which will be held next month on Thursday, June 26th. We will include links to register for part 3 along with links to watch parts 1 and 2 in our follow-up email. Thank you again, everyone, for joining today. And again, thank you, Matt. Have a great rest of your day.